For over half a century, it's been this holy grail for scientists, a dream of limitless, clean energy. And then on August 8, 2021, something truly historic happened. For just a brilliant, tiny fraction of a second, scientists actually ignited a star right here on our planet. So let's dive into how on Earth they pulled off this monumental feat. So what does it take to build a star? I mean, it sounds like something straight out of science fiction, right? But it's the central question, the absolute heart of fusion energy research. And let me tell you, the answer involves conditions that are almost impossible to imagine, and a machine with mind-boggling precision, all just to copy the power source of the universe itself.
Okay, so the whole point here is to harness the exact same process that makes our sun shine. We're talking nuclear fusion. It really is the ultimate dream for clean energy, isn't it? Power with no long-term radioactive junk, no carbon emissions. The big challenge, the one we've been stuck on for decades, is how do you recreate the inside of a star in a building?
So the recipe scientists are betting on is called deuterium-tritium fusion, or DT fusion for short. Basically, you take two heavy-duty versions of hydrogen, they're called isotopes, and you just smash them together. They combine to make a helium nucleus and a stray neutron, and bam! A ton of energy gets released in the process. As far as we know, it's the most efficient way to do it.
And this really gets to the core problem, this constant tug-of-war at the heart of fusion. See, to get things cooking, you need temperatures hotter than the center of the sun. But the moment you do that, your fuel turns into this super hot gas called a plasma, and it's doing everything it can to cool down. It's radiating heat, it's conducting it away, and for decades, the plasma always won. Every single time. It just cooled down way faster than the reaction could heat it back up.
So, to get around this problem, scientists at the National Ignition Facility, or NIF, they tried something completely different. Most other fusion projects use these huge, powerful magnets to contain the plasma. NIF's idea? Forget the magnets. Let's just use the world's most powerful laser and create a tiny star that only exists for a fraction of a second.
And it all kicks off with this thing. It's called a hohlraum. And really, it's just a tiny little can lined with gold. Now here's the clever part. The lasers don't actually hit the fuel. Nope. They fire into this can, and the inside walls instantly vaporize into a plasma that floods the whole space with this unbelievably intense bath of X-rays. We're talking about a furnace on a cosmic scale.
And right in the middle of that crazy X-ray oven sits this perfect little sphere. It's made of high-density carbon, think industrial diamond, and it is smaller than a peppercorn. Inside, there's a frozen layer of that deuterium and tritium fuel. I mean, the level of precision needed to make one of these things it's just mind-blowing.
And this whole thing happens in the blink of an eye. No, faster. We're talking a few billionths of a second. Ready? 192 giant lasers fire. The hohlraum turns that laser light into X-rays, and those X-rays then blast the outer diamond shell of the capsule. They call it ablation, and that creates this rocket-like force that crushes the fuel inwards. It's a perfectly symmetrical implosion at insane speed. But look, just getting the fuel super hot and dense, that's not actually the end goal. The real prize, the holy grail of this whole endeavor, is a concept they call ignition. And you gotta understand, it's not just about hitting a certain temperature. It's about reaching a critical tipping point in the physics of the reaction.
It all comes down to this power balance. See, ignition is that magic moment when the fusion reactions themselves start making enough heat to keep the reaction going. The helium nuclei that are created, they call them alpha particles. They fly out and smack into the surrounding fuel, heating it up even more. When that self-heating becomes stronger than all the ways the plasma is trying to cool down, you get a runaway, self-sustaining reaction. The fire feeds itself.
And this analogy is just perfect. For decades, what scientists were doing was basically trying to light a wet match in the middle of a hurricane. They could get a little spark, they called that a burning plasma. But the wind and the cold, which are the energy losses, would just snuff it out instantly. Ignition. Ignition is when that fire finally catches, when it's big enough to generate its own heat and fight back against the storm.
And check this out. This graph, this is the moment the fire caught. It's plotting the power balance inside that tiny implosion. That big green curve shooting up, that's the heating power coming from the fusion reactions. And all those other curves dipping down, those are all the ways it's losing energy. For the very first time ever in a lab, the heating power just completely overwhelmed all the losses. That massive green peak, that is the signature of ignition.
But let me tell you, getting to that green peak was an absolutely brutal journey. It took a decade of work at NIF, and they were basically walking a razor's edge.
The tiniest, most microscopic error meant total failure. The complexity of what they were trying to do it's just hard to wrap your head around. Okay, try to picture this. Imagine you have a water balloon, and you have to squeeze it so perfectly from all sides that it shrinks down to the size of a pinhead, but not a single drop squirts out to the side. That's the challenge they were facing. The slightest imbalance, a tiny pit on the diamond surface you couldn't even see, a little jet of stuff coming from the tube they used to fill it, any of that could wreck the whole implosion, cool things down, and stop ignition in its tracks.
And this timeline kind of shows you that slow, painstaking process. They tweaked the laser pulse shapes, they called them low foot and high foot, trying to make the implosion more stable. They switched over to these diamond capsules. Then they made the capsules bigger and more robust, and something they called the hybrid design. And with every step, they get a little bit closer, solve one problem, and then slam into a new performance wall. It was this constant cycle, until finally, the hybrid E design in early 2021 got them right to the edge, right on the threshold of ignition.
Which brings us to the summer of 2021. After all those years of these tiny, hard-fought gains, the team got ready for an experiment they labeled N21080. They knew they were close, but I don't think anyone was ready for what was about to happen.
So let's just set the stage here. Take a look at the baseline. The two experiments right before the big one, these were in early 2021, they produced around 0.17 megajoules of fusion energy. Now that was a record at the time for sure. It proved they had what's called a burning plasma, but it was still a long, long way from real ignition.
So you have to ask yourself, right? After a decade of making these tiny, incremental improvements, what could they possibly do to get a totally different result? It feels impossible, but it turns out the answer wasn't some huge revolutionary change. It was a bunch of small, incredibly precise tweaks.
This is where the team just showed incredible finesse. I mean, they were walking that razor's edge. They made the holes where the lasers enter the hohlraum just a little bit smaller to keep more energy inside. They shrank the tiny tube they used to fill the fuel from 5 microns down to just 2, that's insanely small, to reduce any impurities getting in. They got their hands on an even higher quality diamond capsule with basically 0 defects. They even made tiny adjustments to counteract imbalances from the little windows they used for diagnostics. On their own, they seemed like tiny details, but altogether, they were about to change everything.
And the result was just staggering. On August 8th, 2021, that experiment, N2108008, it didn't just beat the old record, it absolutely shattered it. The energy yield jumped by a factor of 8, all the way to 1.37 megajoules. The temperature inside nearly doubled. This wasn't just another small step forward. This was a completely different beast. A phase change. The fire had caught. They had done it. They had achieved ignition. The results were so far beyond what they expected that some of their scientific instruments were completely overloaded. They couldn't even measure it properly at first. It was a genuine Wright brothers moment for fusion. For the very first time, a controlled fusion experiment had, without a doubt, created more heat from fusion than all the other physics were taking away. And this wasn't some borderline call, you know? When they finally crunched all the numbers, they found that this one experiment met the definition for ignition according to 9 different, independent scientific criteria. 9! These were definitions that the community had been arguing about and developing for decades. There was just no doubt anymore.
Okay, so let's be super clear about what this incredible achievement means and what it doesn't mean. They absolutely achieved ignition, a self-sustaining reaction. Check. They also got really close to what's called scientific break-even. That means getting more energy out of the fuel than the lasers put into the hohlraum. They got about 72% of the way there. But, and this is the big but, this is not a power plant, not even close. There's still a really, really long road to go to get more energy out of the whole system than you put in to run the lasers in the first place. You know, for more than 50 years, the fundamental question was always, can we even light the fire? And on August 8th, 2021, the answer finally became a resounding yes. This single experiment proved that the physics we thought would work actually does work. It proved that what seemed impossible is in fact possible. So the challenge has now changed. It's no longer about starting a star, it's about figuring out how to keep it going, and one day, how to use it to power our entire world.